When sugar is metabolized in the body, the sugar reacts according to the following equation. C12H22O11 plus 12O2 yields 12CO2 plus 11H2O. This is the typical combustion reaction. For the reaction as written, the delta H of that reaction, the standard delta H of that reaction is negative 5650 kilojoule, and the standard delta G of that reaction is negative 5790 kilojoule at 25 degrees Celsius. What is the maximum amount of work that can be done when 1 gram of sugar is metabolized at body temperature, 37 degrees C, if 25% of the free energy change is available to do work? Part B, a 55 kilogram woman wishes to climb a mountain. How many grams of sugar per meter of vertical distance to be climbed needs to be metabolized in order to accomplish the climb? Right, so take in a little bit the givens in this problem, and now the solution will be elaborated. Okay, so the first thing that is going to be done is use of the Gibbs-Helmholtz equation at 25 degrees Celsius. Why? Because delta G of the reaction at 25 degrees Celsius was given, and the delta H of the reaction at 25 degrees Celsius was given. So given the temperature at 25 degrees Celsius, 298.15 K, the only unknown is the delta S of the reaction at 25 degrees Celsius, 298.15 Kelvin. So solving this equation for delta S of reaction is equal to negative of the quantity, delta G reaction minus delta H reaction divided by T. When those values that are given in the problem statement are substituted at the temperature of 298.15, then the delta S of the reaction is found, and that delta S is 0.46956 kilojoules per Kelvin. So this was done because in order to obtain the free energy change for the metabolism of sugar at 37 degrees Celsius, the entropy change of the reaction is computed at 25 degrees Celsius, so that its value may be used to compute the delta G of the reaction at 37 degrees Celsius, using, again, the Gibbs-Helmholtz equation with constant delta H and delta S. So this is very important. So while the equations are simple, the interpretation could be confusing. So now the Gibbs free energy is the maximum amount of non-PV work that a system is capable of performing at 37 degrees Celsius, which is 310.15 Kelvin, and for constant delta H reaction and delta S reaction. The delta G reaction now can be computed at the new temperature, meaning at the body temperature, 310.15 Kelvin. So, putting in the values of the delta H that was given, along with the delta S that was computed at 25 degrees Celsius, and now using the new temperature, 37 degrees Celsius, 310.15 Kelvin, the delta G of the reaction may be computed. The delta G of the reaction, as written, is now found to be negative 5795.63 kilojoules. And since the chemical reaction has only 1 mole of sugar, therefore the specific delta G, the specific standard delta G of the reaction is negative 5795.63 kilojoules per mole. Okay. So this is a very important computation because it emphasizes the fact that for the purposes of this problem, the delta H, the standard delta H of reaction, and the standard delta S of reaction are taken to be independent of temperature. In reality, they aren't. But this is a very small temperature change, so they are taken to be constant. However, delta G is a very strong function of temperature. and that cannot be taken to be constant with temperature. Okay, so this is now the delta G of the reaction at the new temperature. The quantity that has therefore been computed is the total Gibbs free energy change for the reaction as written at 37 degrees Celsius. Now, for the metabolism of 1 gram of sugar, what is done is computation basically of the molecular weight of the C12H22O11 molecule and figuring out how many moles that represents. Okay, so 1 gram of this molecule divided by its molecular weight equals the moles. So it's a very small amount of moles of the sugar molecule. So therefore, the standard delta G for the combustion of only 1 gram of sugar is therefore this quantity of moles, so 2.92107 times 10 to the negative 3 moles, times the delta G of reaction per mole. So negative 5795.63 kilojoules per mole. Multiplied by that amount of moles will give the amount of kilojoules. Okay. So the answer is negative 16.9294 kilojoules. That is the delta G for the combustion of 1 gram of sugar. That's delta G. It's negative because the energy is released. The energy is released, and therefore that same amount of energy is available to do work. In which sense? Well, the Gibbs free energy is the maximum amount of non-pressure volume work that is available to be done upon the combustion of 1 gram of sugar by the body, which is in this case 16.9294 kilojoule. So that energy can be used to do a certain amount of work. Okay. And now, if furthermore, only 25% of this amount is actually converted to work, because this is energy, right? Not all energy can be converted to work. So if 25% of this energy is converted to work, then the amount of work that can be done is 0.25 times 16.9294 kilojoules, or 4.232 kilojoules. And that is the answer for part A. Now for part B, the given is that there's a 55 kilogram woman. She wishes to climb a mountain. And the question is, how much sugar, how many grams of sugar per meter of height climbed is required? Okay, so we need grams of sugar to be metabolized per meter of height climbed for a 55 kilogram person. What is known is what was known from part A, that 4,232 joules are available to do work per gram of sugar that's metabolized. Okay, now 1 joule is equal to 1 kilogram meter squared per second squared. So alternately, this quantity here, 4,232 joules divided by gram sugar, is equal to a certain amount of work per gram of sugar. Okay? Now, recall that the work of potential energy is equal to mgh, where m is the mass of the person or the object doing the work or upon which the work is done. G is the gravitational constant, 9.81 meters per second squared, and height is the distance climbed. So if this equation is simply divided by grams of sugar, because this is what I have, work per gram of sugar is equal to mgh divided by gram of sugar. That's very convenient, because what I would like is grams of sugar per height. In other words, grams of sugar per meter climbed. So I'm going to take this quantity, put it on the left-hand side, and I get grams of sugar per height in meters is equal to mg divided by this quantity, which is work per gram of sugar. So that's the equation I need, right? I need grams of sugar divided by meters, divided by the height that's being climbed. So now I can just plug in the values. Mg, 55 kilogram, g 9.81 meter per second squared. The work that's available upon the combustion of 1 gram of sugar, 4232 kilogram meter squared per second squared over gram of sugar will give me what? Will give grams of sugar per meter. Okay, grams of sugar goes up here, then it's per meter, okay, because meter divided by meter squared is 1 over meter, and that is 0.1275 gram of sugar per meter. So, in other words, to be able to climb 1 meter, 0.1275 grams of sugar need to be metabolized. As an example, to climb a mountain that is 4,000 meters high, the 55 kilogram person needs to metabolize this quantity of sugar, 4,000 meters times 0.1275 gram sugar per meter, or 510 grams of sugar. That's like half a kilogram of sugar that needs to be metabolized. That's a lot of metabolism going on. So in other words, if one wants to climb a mountain, please do not do it on an empty stomach. Any questions? Please put them in the comments below. Stay safe. Happy mountain climbing.